Okay, everyone. Now we'll start today a very important lecture that about strain gauges and load cell. Okay. Now this course is I'm trying to mix between the tools. The tools means the circuit analysis technique and the main objective of the course, which is to teach you how the sensors that in your field works, how you can use them, how you can connect them, etc. So today we'll start with one of the most important sensors, which is the strain gauges, and we'll spend some time how to analyze their circuit. And here the Wheatstone bridge become very important concept here that you need to understand. And it is the application actually of Wheatstone bridge. The main application is in the strain gauge, as we'll see. Then we'll talk about something called the load cell, which is nothing but basically a combination of strain gauges. Then we will cover briefly some type of sensors with the same category as the strain gauges. Okay, so let's start. Okay, stress and strain. These are some terms used by civil engineers, stress and strain. So a stress is when you have, it's the force per unit area of a material. So when you apply a force on a material, this is called a stress. As a result of the stress, there will be a strain. This strain is extension per unit length of the material. As a result of your stress, there will be some strain coming out of the material. Now, if we apply a tensile force, then you will have a tensile stress and hence a tensile strain. Vice versa, if your force is a compressive force, then you will have, on the other hand, you will have compressive stress and compressive strain. Okay, so if we want to draw here the stress versus strain, okay, and if we define the stress as sigma force over area, so if you have the material here and this is the area and you're applying a force, either a tensile force or a compression force, so this force that you apply divided by the area is what we call the stress. The strain is, as a result of this force, there will be change in the length of this material. Okay, this could be positive or could be negative, meaning you could increase or decrease the material depending, are you applying a tensile force or a compression force. Now if we draw the stress versus the strain, the more stress you apply, the more strain you get. So it is have a sort of a linear relation. So as you apply more and more and more and more and more stress, you are getting more and more strain. Now, this will take us to what some important terminology used by civil engineers called the Young modulus, which is capital E, which is the stress over the strain, or sigma over epsilon. Now, this linear relation, we see it here, is only in certain range. If you keep on increasing, then the material will start to lose its elasticity, and eventually you will have a fracture of the in the material. Now, why we need to measure the strain? Okay, the strain that is a result from the stress. For example, if we have a bridge and this bridge becomes very old, so if we want to know if this bridge start to yield, the bridge start to get some deformation, so that we can detect that at an early stage, and hence we can prevent this from happening. Also, for example, the rails, we want to make sure here are some strain gauges connected here. We want to make sure that they are not deformed, because if they start to deform, then the train may get an accident. We sometimes we heard in the news a train went away from its path or its rail. Why is that? Because those beams start to deform because of many factors, because of the continuous environmental condition, because of they are old, because of the stress on them coming from the trains. Then they start to deform, and then the train at certain point they might lose the track. Okay, so we need to know if these are deformed. So we need a sensor that is very sensitive, that can measure not a huge strain, but even a very little strain, because this can make a big difference. And this is our strain gauge. So this is our strain gauge. This is how it look like. It's a very small piece of material, and it measures the change in length over a given length. So if you have a given length and there is a small change in the length, we can measure this using the strain gauges. So one of the advantage of the strain gauge is very small, and hence it has insignificant mass. So if you put it on the material that you want, on the bridge or on the rail, it does not by itself exercise a stress. Otherwise it will be bad. If it's a heavy material, then you will have a stress coming from the sensor itself, and this is not the case. Very highly sensitive, which is very important, because here, remember, we are measuring strain in, let's say, steel structure. We don't expect the steel structure to act like a rubber band where you have a huge strain. The strain will be very small, so you need something that is very sensitive, that can measure such strain. Again, because this is will be usually in outdoor conditions. We have seen in the previous slides, we have them in bridges, on railways, so they have to be immune to the environmental condition, regardless how harsh these environmental condition. It should have a good static and dynamic response. Static response means a response to the change in the on the material strain on very slow. Okay, something that is coming with months or with years. So if you want to monitor this, or dynamic response, if you want to see something, how it respond, for example, due to an earthquake, okay, or something very fast force that is applying on the structure, then you need to have something that is very dynamic, means it can sense this huge changes that happens in a very short period of time. Inexpensive, and indeed it's very inexpensive. So what is it composed of? It's composed of two main things. First, the metallic wire. You see here these are the two terminals, and here we have the wire. You can see here the wire go all the way around. So there is a wire, as you can see here. And the strain gauges, this wire, if you measure its resistance, it has standard resistance value 120 ohm, 350,000 ohm, and the one that most common used is the 120 ohm. Now, this is a resistance, actually. It's a wire. The wire has certain resistance. And we know that R, resistance of a wire, equal to rho L over A. L is the length, A is the cross-sectional area, and rho is the resistivity or a material property. Okay. Now, this wire, we will have some voltage applied to it. There will be some current applied to it. So when it touch a metallic structure, it will be like a short circuit. So how you have to isolate this wire from the structure that you are measuring, and hence we have a backing material. This orange material is an electrical insulation, so it will insulate this black wire from the structure it sends. Okay, so this is very important. And also this material can transmit in a very efficient way the strain that happened on the structure to the wire, so it will not absorb these changes, otherwise the sensor becomes ineffective. And this backing material, as I mentioned, the sensor will be in outdoor conditions, so it has to be very robust when it comes to harsh environmental conditions. I encourage you to go and watch these two video tubes. These are how to install them. And this is a beam here, and you can see here is this is the Wheatstone, sorry, this is the strain gauge, and there are two terminals coming out of it that is will be used to measure the electrical properties of interest that we will talk about in a few seconds. But I really encourage you to go and watch these video tubes. It will give you a practical idea how we install them. You will see them physically, and you will appreciate more this type of sensor. Okay, now let's see the calculations. As I just mentioned, R equal to rho L divided by A. So what is the principle here? How it works? So this is a wire. This is the wire. Remember, the strain gauges basically is a long wire like this between, let's say, terminal A and terminal B. Okay, so you have a wire that has its resistance. That is a function of the cross-section area and the function of the length of that wire. Now, if we stretch the wire, what will happen? Two things will happen. Your L will increase and your A will decrease. So both these together will result in an increase in the resistance. So let's go back at the first week when we talk about a sensor. What is a sensor? A sensor is a device that convert a physical phenomena into an electrical phenomena. So here, the strain, which is a physical phenomena, is changed, converted to a change in the resistance. So for you, you will not measure this change in length of the beam because it's very, very small. However, you will measure the change of the resistance of the strain gauge, which is somehow correlated to the deformation that happens. Now, if you apply a compression forces, the opposite will happen. Your R is equal to rho L over A. So if you apply a compression forces instead of a tensile force, your L will decrease, your A will increase, and then your R will decrease. So this is how you can even distinguish between a tensile force and a compression force, and we'll see that more in details soon. Okay, so this is a strain gauge. This is how it look like. This is when there is no any pressure or any force on it. Now we have two types of forces. We have tension force or we have compression force. So let's assume that I have a beam like this, and this beam will have this small strain gauges here. So if I apply a force in this way, the beam will start to bend this way, and the strain gauge attached to it will start to be stretched. So your resistance will start to increase, not to decrease. On the other hand, if I apply the force in the opposite direction, then the beam will start to deform in this shape. And when it comes in this shape, your strain gauge will be somehow compressed. So your resistance will be decreased. So here, your R will go up if you have a force in this direction. And if you have a force in the other direction, then your R will decrease. So this is something fundamental, very, very important to understand. And we'll use this fact when we derive the formula for the strain gauge. Okay, so let's do the math now. And your R, as I said, your R is equal to rho L over A. I will multiply by L over L. So this will give me rho L square, rho L square over A times rho L square, okay, over A, okay. Now let me take the derivative of this. what will be your, oh yeah, there is an L here. So here, rho L over A, this is your resistance. I will multiply by L over L. Okay, so here you will have rho L over, so this is what becomes your L, A here. You can see the formula here. So this becomes the volume. Okay, so A times L, or this becomes rho L squared divided by the volume. Why the volume? Because if this is your wire, so this is your A and this is your L, and you look this as a cylinder. So in a cylinder, the cross-sectional area times the length is the volume. So it becomes rho L square divided by the volume. Okay. So here it is your formula that you have. Okay. Let's move on. Now, if I take the derivative, now again, R is equal to rho L square over the volume. So let me take the derivative dr by dl. So I will take the derivative with respect to L. This becomes 2 rho L divided by V. Okay. So this is your dr by dl, 2 rho L divided by V. Now again, I will multiply this dr by dl with L divided by L. Okay. Now we know that R is equal to rho L square divided by V. So rho L times L over V, all of this is nothing but R. Rho L times L over V is R. This is from the previous formula. So I can say that dr by dl is equal to 2R divided by L. Now I can take R to this side, L to this side, so you can say the following. dr by R divided by dl by L is equal to 2, and this is, we call it the gauge factor. And this is something very, very important. Let me ask you a question. Do you want this to be as high as possible or as low as possible, and why? This number 2. Do you want it to be as high as possible or as low as possible, and why? High. Why high, Kelly? Why you think that should be high? Excellent, 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 Chloe. This is for better resolution. Remember, here the what is this formula? Let's understand this formula. dr by R, this is the change of the resistance over the actual resistance of the sensor divided by the change of the length over the actual length. I want this to be as high as possible. Why? Because this change is reflected as a change in the resistance. And I want for a small change in the length to have a bigger change in the R, in the resistance, to be able to measure this. Imagine if DL for a change by 1 meter, my resistance will change by 0.00001 ohm. So this is really bad, because what if the change is 1 centimeter? Then I cannot measure anything. So I want the change in the resistance as a reflection to change in the length to be as high as possible. And this ratio is called the gauge factor. So this gauge factor, as I said, dr by R divided by dl by L. But we said that this dl by L is actually the strain. So it's dr by R divided by the strain. And this is your gauge factor. And it is the sensitivity of your material. Now, most of the materials around 2, but there are some advanced materials, they have very, very high gauge factor. So here, this is a table for different materials. it's used and their composition, and this is the gauge factor. So you can see here the gauge factor is 2, but for some material it is extremely high, some negative, some positive. Okay, and this material is actually called semiconductor. Okay, we will not deal with this because this is more of electronics. So this one we will not deal with those type of materials, but we will use the basic material that is made from the regular conductors. Okay, let's see this straightforward example. I have a steel bar. Okay, and this steel bar has a cross-sectional area. This is a cross-sectional area. It's 2 by 1 centimeter. Okay, is subjected to a tensile force 20 kilo Newton. So there is a tensile force 20 kilo Newton. A strain gauge is placed there. Find the change of the resistance of the strain gauge if it has a gauge factor of 2 and the resistance was originally 120 ohm. So if I apply this force, 20 kilonewton, how much I will have a change in the resistance? The Young modulus of the elasticity of the steel is equal, so it gives you also the Young modulus. Okay. So here, this is your strain gauge. This is the Young modulus. The force is 20 kilonewton. The area is this. The R is equal to this, 120 ohm. Now, the stress is the force divided by the area. So we have the force, we have the area. So it gives you the force divided by the area. Now, the Young modulus is the stress over the strain. And from this, I can get the strain, which is the stress divided by the Young modulus, which is equal to this. Okay. Also, we know that dr by r is equal to lambda dl by L. This is from the definition of lambda. Lambda is equal to dr by r divided by dl by L. Okay. Now this is equal to lambda. dl by L is nothing but your strain, which is epsilon. So your dr, the change in the resistance, is equal to lambda epsilon times r. And now we have all the values. This is equal to 2 times 5 times 10 to minus 4 times 120. And this will give me a very, very small value, which is 0.12 ohm. So originally I have 120 ohm, but the change in the resistance because of this 20 kilonewton, this is a huge force, is just 0.12 or 0.12 ohm. Okay, excellent. Now, let's see. Now let's go to the practical thing. How I will measure this change. Okay, will I have a ohm meter to measure the resistance, apply there and wait for the measurement? Remember what we said. We said that we want to have continuous monitoring. And also 0.12 ohm, this is very, very little. What if the force is much less than that? So the change will become very, very small. Okay. So this is not very practical to go and measure the resistance directly. However, we can measure it using the Wheatstone bridge. Now, let's try to refresh our memories about the Wheatstone bridge. We said that the bridge is balanced if R1 over R2 equal to R3 over R4. So what we do actually, here we install a regular resistance. Let's say this is 120 ohm. And this is a regular resistance, 120 ohm. And this is the strain gauge, 120 ohm. And this is a variable resistance. We set it to 120 ohm. And the variable resistance is something called like this, shows like this. So resistance, you can adjust its value to a very, very nice or very, very fine-tuned value. Okay, now if I apply a stress, this will change. If we apply the stress that we talked about, so it becomes 120 plus a change in R, let's say delta R. So if, and I don't know this delta R, and I don't want to go and measure the resistance. I don't want to do that because that's not really practical. I need to have a very precise ohm meter, and I don't want to do that. However, if I measure the voltage here, I will see if the voltage is not zero, then it means that the bridge is not balanced. So what I will try to do, I will start to change this resistance R1 until I get V equal to 0. So I will start playing with the values, okay, until I get a 0. When I get a 0, it means that, because as I said, R1 over R2 has to be equal to R3 over R4. This is 120, this is 120, then it's equal to 1. So if there's any change happened here, if I match this change in R1, this means that R1 and R2 will be equal. So I know R2 indirectly. By knowing R1, I will be able to know R2 without the need to measure its resistance. So this is how it works. But again, this is not practical. Why it's not practical? It means that someone has to sit there and do every time there is a stress, the adjustment. Remember, our strain gauge is installed somewhere in the site. It's not practical to have someone with this circuit and every time the voltage becomes not zero, the bridge becomes unbalanced, meaning there is some stress applied, then I start to play with the resistance to match and to see how much that change. That's not practical. So this is why that's not the best method. Okay, now we know that we measured the voltage here, if you recall. Practical means that in the field, if you are in the lab, you can do this. There's no problem. You will be there in the lab, you have your strain gauge, you apply the stress, R will change, match the resistance, measure the voltage, make equal to 0. That's no problem. But if you are in the field and you want to measure continuously the strain happened on your bridge, it's not practical, because you can't have someone 24/7 waiting for any stress to happen and then do the matching in the circuit. You want to monitor this continuously remotely without the need to send someone physically to be there. Okay, so to do that, instead of measuring the change in the resistance, we can measure the change in the voltage. And we know that this is our formula. Whenever there is any change happened in the whenever the bridge changed from being balanced to be unbalanced, we know that is the formula. If it is balanced, V out, we know, is equal to 0. But if there is any change in the resistance and R1 over R2 not anymore equal to R3 over R4, then you will have a voltage that you can measure. So what we do, we start with a condition of balanced, meaning V out is equal to 0. And then once there is a change in the resistance, somehow we will see different configuration in the coming slides, then we will have a V out. The question is, what is the correlation between the change in the resistance and the change in the voltage? This is extremely important. I want to know, for this change, there will be this change in the voltage. So I'm measuring voltage, but this voltage is actually a reflection of a change in the resistance, which is a reflection in the change of the strain. So I'm changing the strain to a change in the resistance, and then the change in the resistance is a change in the voltage. Now, Okay, so what's special about the voltage? Because this voltage now, I can measure it using many types of, you will see that you will measure the voltage using your microcontroller. So you could have a microcontroller measuring this, and then you can have either through cable or through wireless communication, send the values of the voltage continuously to some laptop that is far away from the field. So you will be in your laptop, you will receive those values continuously every 1 minute, every 10 seconds. It's up to you how much frequently you want to measure the voltage, and you don't need to go there. So the question is now, what is okay, the values is a very good question. Why the values of the resistance cannot be sent? Because all the measurement systems that we have are based on voltages, not based on the resistance and even currents. Even if I want to measure a current, I have to convert it to a voltage. So everything is based on voltage measurement. There is no device in the market at all that measure the resistance and then transmit the value as a resistance. Always it has to be a voltage. Second thing, which is very important, how you measure the resistance here practically. If you want to measure the resistance practically, you have to connect something here in parallel with the resistance. This is your ohm meter. But this resistance is not the value of this resistance only. It's the value of this R in combination with all other resistors, because they are in series and in parallel. These two are in series. This with the rest with everything is in parallel. So, and there is the resistance of the wires, the resistance. So the resistance is not a good way to measure this. But the voltage, no, the voltage is not interfering with anything around. Okay, now let's go for the real deal, and let's now derive the formula. Imagine we have the following. We have a Wheatstone bridge. R1, R3, and R4 are all regular resistors. So the resistors has nothing to do with the force. These are the resistors that you have them in your kit. And only R2 is basically will be a strain gauge. And you apply a force as you can see here. So your R2 will be changing to delta R2, or we can say as to delta R. Why increasing? Because the force will lead to the when it applies like this one, the deformation of the beam will be as such. So your strain gauge that is attached to the top here will be stretched. There is no specific reason why R2. It could be R1, R3, or R4. It doesn't really matter. It could be any of those. So there is no specific reason. Thank you for the question. It is R2. Okay. Now let's derive the formula. If we have this change in delta R, so your V out, yeah, it's just random. Exactly. V out is equal to, this is now the Vs times R3 plus R2 minus R1 times R4 divided by, this is the formula, R3 plus R4 times R1 plus R2. Now R2 will change from R2 to R2 plus delta R2. So now this is after when we apply the strain. So this is becomes Vs R3 plus R2 plus delta R2, okay, minus uh, sorry, this is multiplied, not sorry about that. So this is just multiplied. So this is like this, minus R1 R4 divided by R3 plus R4 times R1 plus R2 plus delta R2. So the only thing I did, I came to R2, I change it to R2 plus delta R2, nothing else. This is the only thing, R2 here and there. I change it to R2 plus delta R2. Now let me open assume that all the R's, R1 equal to R2, equal to R3, equal to R4, equal to R. So all of them, they are just R. And then we'll have delta R. So let me, and this is very practical. You can select all of them have the same value. So Vs, this becomes R times R plus delta R minus R times R divided by R plus R times R plus R plus delta R. So nothing specific here. So I just changed everything uh, to R, except for R2 becomes R plus delta R. So this becomes Vs times, let's multiply, this becomes R squared plus R delta R minus R squared divided by 2R times 2R plus delta R. So this becomes equal to Vs. R squared will cancel with R squared, so this becomes R delta R divided by. Now, to make a little bit of approximation here, we said that the R is in the range of 120 ohm. We have seen that the delta R is a fraction of this. So it's like 0.1, 0.5, something very, very small. So delta R becomes like around 240. And this is very, very small. So we can say that R plus delta R approximately is equal to R, or 2R plus delta R is approximately equal to R. This is just to make the formula look nicer. So this becomes 2R and this is 2R, and we'll ignore this one. So this becomes 4R squared. Then R will cancel with the square. So the change in the voltage will equal to Vs delta R divided by 4R. And this is your V out. Now what I want to find, I want to find delta R. Now, V out, something I measure. 4R, the R, I know it in advance. Vs is the supply here. So I know everything, and then I can find my delta R. So here, everything is here. Now, at the end here, I give just some typical values. So if all resistors equal to 120 ohm, delta R is equal to 0.12 ohm, as we have seen in the previous example. Vs is 10, sometimes 5 volt. Then your V out is 2.5 millivolt. Very, very small value. And we need to do something about that. Okay. Now, let me ask you this question. So this is your output, Vs delta R over R. What will happen to this formula if the force, instead of I applying it from up, down, down, up? What do you think what will happen to this formula? If the force is applying from bottom up, becomes negative. Excellent, 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 everyone. Becomes negative. So even if I apply the same force, I will get a negative voltage. And this is extremely important because I can tell if the force going from up down or down up if I know the sign of the voltage. So I'm not just telling you how much change in the resistance, but also the direction of the force. So I can tell both direction of the force and the value of this. So this is very important to understand. Let me see if you have any question. Is that because it would compress? Yes, exactly. Now, when you apply the force in the other way around, the beam, instead of being stressed this way, the stress will be the other way around. Okay, and this strain gauge will be compressed because the beam itself now is going in the other way around, and it is deformed in this shape. becomes this shape. This is typical values. This is just typical values. 0.1 to 0.5, just a typical value. Just I'm giving you a rationale why we ignored the delta R in this formula. Just giving you typical value. This is like 240. These are fraction of 1 ohm. So if I remove the delta R, I'm not really changing too much the formula. That's all. This is the whole reason why I'm giving you this typical value. Hopefully this is clear. Okay. One last case. Now, you will have a question like this in the midterm. And the question, you will have different configuration. Let me give you another example. This example. Now I will have two strain gauges, not one. So R3 and R4 are regular resistors. But now, for the same beam, instead of having only one strain gauge at the top, I have one at the top and one at the bottom. So what will happen? If my force is going this way, then your R2 will be R2 plus delta R2. And on the other hand, your R1 will become R1 minus delta R1. So this is something very, very important to notice. And that is the only thing you need to know, by the way. The only thing that you need to know is my R increased by delta R or decreased by delta R? That's it. This formula doesn't change. V out equal to Vs R3 times R2 minus R1 times R4 divided by R3 plus R4 times R1 plus R2. This is a unique formula. So you need to identify which R's are a fixed resistance, means nothing will happen to it, and which are good, which are which are will be a strain gauge, and this the one that will be changing according to the force. This is the first thing you need to know. The second, you need to know this R, am I adding a delta R to it or subtracting a delta R from it? If I am adding a delta R to it, then it will then if the strain gauge is uh, the force on it elongation force, then this means that it will be increasing. If it is compression force, then it will be decreasing. Now again, I will assume that all the resistors R1 equal to R2 equal to R3 equal to R4 equal to R, and delta R1 equal to delta R2 equal to delta R. I don't want to move here until I make sure that everyone understands. How do you know if you are subtracting or adding delta R? Again, it depends. Remember, the R, your resistance, is nothing but the how your strain gauge is interacting with the force. So if I am stretching my strain gauge, I am increasing the resistance. If I am compressing my strain gauge, then I am reducing the resistance. That's you need to tell. So if you look here, this beam will be coming like this. Okay, because of the force coming from up. It is a cantilever force, so the beam is fixed from this side and applying from other side. So this will be how it will look like. Now, if it look like this strain gauge will be elongated, will be stretched. This strain gauge, on the other hand, it will be compressed because it is at the bottom. Okay, so this is why we can tell if the strain gauge is increasing or decreasing by delta R. So let's derive here. V out equal to Vs. It doesn't matter which one to be a strain gauge, but you have to know R1 is at the bottom. Yes. Don't be fooled here. It is epsilon 2, epsilon 1. So this one is at the top. So don't be fooled by their order here in the string gauge. It doesn't really matter how you order them, but you need to know which one is in top. So this is epsilon 2 and this is epsilon 1. So this is R3 doesn't change. So this is case stays at R. R2 becomes R plus delta R. So this is R plus delta R minus R1 will change to R minus delta R, but R4 nothing will happen to it because a regular resistance is R divided by R plus R. So this is R plus R, nothing will happen to them, times R1 is R minus delta R, R2 is plus R plus delta R. So Vs R squared plus R delta R minus R squared plus R delta R divided by 2R times this will cancel 2R. This will cancel, so you'll have here 2R delta R divided by 4R squared. So this will cancel. So this becomes delta R divided by 2R. If you recall from the previous formula, it was delta R divided by 4R. So here I am increasing the voltage, more bit higher voltage for the same force by just switching one of the resistor to become another string gauge, which is something good for me. So if you do that, if you apply the same numbers, you'll get the V out is equal to 5 volt. Okay, now we have very little time. Let me ask you my bonus question. And I want you to think about it very, very well. Okay. My bonus question is as follows. If my force is not vertical, if my force is, on the other hand, in this way, so I'm pulling it, I am pulling the beam, what will be your V out? Okay, that's not the only thing. What will be the V out? And if this is acceptable or not acceptable. So what will be your V out, the value, and if this is good or bad. Voltage will increase delta R over 4R. Okay, this works. Okay, think about it, guys. Look to the formula and see what will happen. It will act as compression. Stretch the wire. Voltage is negative. Okay. Does the string gauge have to be perpendicular to the... No, it doesn't have to be. The string gauge is attached as such. So I am now the force. You are right, Carter. Emmanuel, both are correct. So what will happen? So both R1 and R2 will be stretched. Excellent. So is this good or bad? The voltage will be 0 if this is bad. Bad, bad, bad. Okay, now it's very hard for me. It's very bad for me because I don't know who said what first. Let me see who the first one said bad. Okay, Dean. Uh, Dean Shujat. Okay, I will give you the chance, Dean. Why it's bad? To answer this, to get the bonus. Why do you think it's bad? Okay, guys, I am very happy. Indeed, I'm very happy. You guys are interacting and you guys understand the concept. But Dean, if you don't know, then I will ask someone else to give me the explanation. Why? Because, okay, excellent. Okay, now, so, okay, Dean, please send me an email after the class. You get the bonus. Let's see here. When you stretch the force, you stretch the beam, sorry, both R and 1 and R2 will have this R becomes delta R and this becomes R plus delta R, because when you stretch it, both of them will increase. When you come and substitute here, so this becomes plus. So if this is plus, this becomes minus, so you will get 0. So although you apply the force, you're still getting a 0 volt. So you will be fooled because you think that the system is balanced. There is no force. You want that if there is any force to get a voltage. But now, if you apply the force as such, then that will be too bad for you because it will be stretched and sorry, it will be cancelled out. And regardless if you have a force or if you don't have a force, then you get a 0 volt, and that's not really desirable. I want to have it when there is no force, the voltage is 0, everything is balanced. Whenever I apply the voltage, I have to see the change in the resistance as a change in the voltage. If I keep getting 0 volt, then that's not good for my system. I will stop here. Okay, let me first stop the recorder.